Okay, good morning. Let's pick up where we left off. So we had been talking about how to solve quadratic equations. We learned about the zero factor property. We learned about completing the square. We learned about using the quadratic formula. And we also learned that you can factor sometimes to help you solve, but that it doesn't always work. And that's okay. You still have other techniques that you can lean on just in case, right? So what we are ready for now is graphing quadratic equations. There's just a few parts that you really need to make sure that you take into account. I also want to stress notation. So as we move into this section, it's going to be really important for you to really notice the notation and kind of use that again and again to help you in this process, okay? As always, if you do have any questions, don't hesitate to ask. But yeah, let's get through this. As soon as we're done with our Unit 4 notes, which I would imagine we'd be done early because there's only a few pages left, we'll take our break and then we'll resume with Unit 5. Now with Unit 5, I do intend on skipping a lot of that material because when you look through Unit 5, like if you had a chance to kind of breeze through the notes, you probably saw that it was a lot of 098 content, and I don't want to redo 098 content. We simply don't have time for that. But I also don't believe that you really need that entire 098 content again. So I think you're going to be just fine. All right, let's take a look. Graphing quadratic functions. First off, when you graph a quadratic function, it looks like a parabola, like a U, like it's either open upwards or it's open downwards. Now you'll know whether or not it's opening upwards or downwards because of the leading coefficient. So when you look at this A, your leading coefficient, if that's positive, if A is greater than 0, it's going to open upwards like a smile. So this is going to be really, elementary, but you see here how this is opening upwards. So it's kind of like a smile. If your leading term is a negative, where your A is less than 0, then it's going to be concave downward. So I want you to think of your parabola being this shape now, right? So it almost looks like a frown. Silly, but it works. It's an easy way to remember this. The direction of the opening only relies on your A. So you look at this one, you say, okay, positive, opening upwards, negative, opening downwards. If your parabola opens upward, that means you have a minimum. That's very important to keep in mind. If your parabola opens downwards, that means you have a maximum. Just something to consider when we get ready for application problems, which you love, right? Word problems, they're the best. Yay. Okay, anyways, sorry. All right. When we graph quadratic functions, we need different parts of the quadratic formula to help us, right? So for instance, one of the things that I talked about in my previous video is that your parabola is actually symmetric about the center. So for instance, if I took my pencil and I drew a dotted line through the center, do you see that it's completely symmetric about this line? That means this line is called the axis of symmetry. So for instance, if you are, 2 points away on the left, you're going to be 2 points away on the right. If you're 4 points away on the left, you're going to be 4 points away on the right. Okay, so your points in a parabola, they're completely equidistant from the axis of symmetry. Now, what the hell is the axis of symmetry? Would you please circle this part of your formula? This part right here. Ooh, there we go. X is equal to negative b over 2a. That is the formula for the axis of symmetry. So we're going to actually write that here. X is equal to negative b over 2a. Now I want you to think about this logically. Our equation reads x equals. So when we find the axis of symmetry, we're finding an x equals a number equation, right? What we learned way back when in 098 is that if we had the equation, let's say x is equal to 2, that's a vertical line. right? So if we had x is equal to 2, that would be a vertical line. So that would make sense that it would represent your axis of symmetry. The other thing to consider is take a look at this graph that I have here. If I follow this axis of symmetry until I hit the parabola, so until I hit this minimum, this vertex, that axis of symmetry equation gives you the x coordinate, which is actually really cool. We know that in order to find a y coordinate, all you have to do is plug in x. So we would essentially say, well, if I had my function, all I have to do is plug in that x so that I can find its corresponding y, which then gives me my minimum. Same thing with the max. Okay. Having said that, your vertex is the ordered pair, your x from your axis of symmetry, f of x, right? You would evaluate. So let's say take your x coordinate found from the axis of symmetry and plug this value into your function to find its corresponding y value. It's kind of cool how this idea has never changed. If you want to find a point on a parabola, on a graph, on a line, on whatever function this is, if you want to find a point, well, you plug in an x value and you calculate its corresponding y. That has always been the case. That has never changed. This is the exact same thing. The only thing is, in order to find the vertex, your x is directly the axis of symmetry. Another way to write this, and hopefully this doesn't freak you out, but that implies that your x coordinate is negative b over 2a, and that your y is evaluated at that point. Okay, it's just a fancy way of saying take whatever x you have, plug it in, solve for y. Okay, don't panic about that.
I'm sorry, I just got really confused. Can you repeat that for me, please?
Yes, yes. When you want to figure out where your vertex is, you're always going to take your axis of symmetry, whatever this number gives you, right? It's going to be a value. And that becomes your x coordinate. Now, all you do to figure out its y, its corresponding y, is you take that x coordinate and you just plug it right into the equation that you're given.
Oh,
right?
Okay. Sorry.
Yes, beautiful. Always think input, output. You just plug in it right into the equation. Good. In addition to finding your axis of symmetry and then your vertex, you also want to find your x-intercepts. So I want you to think of these as your zeros. We've learned how to find x-intercepts. First off, we can do that by calculating the x value when y is 0, right? And the only way that we can do that with a quadratic function is we can consider maybe factoring then solving. I can't even talk. Factoring then solving. That might work. Or we can say, maybe that's not going to work. Let's complete the square. That will always work. Or maybe you don't really like completing the square. Maybe you're like, I like the quadratic formula better. And that will also give you your zeros. But your x-intercepts are always the form, your x value, comma, 0. That's really, really important to know. And you already know that the x-intercepts are where the graph crosses the x-axis. This is a recap of 098. You've seen this before. So for instance, I'm just gonna scooch this up for a moment. If we look at our graph here, our parabola, our x-intercepts are at these 2 points. These 2 points that I circled represent our x-intercepts. In this case, we have 2. We also have a y-intercept. That's simply where the parabola goes through the y-axis, and the y-intercept is located here, again, where the parabola crosses the y-axis. For your y-intercept, it's always of the form 0, comma, whatever that y value is. So that means if you plug in a 0 for x, you can easily find the corresponding y value. Plug in a 0 for x to find y. Okay, cool. And again, that is a recap of 098, that part. Good. As a reminder, if you are curious whether or not you actually had 2 roots, 1 root, or no root, we learned about this last time, you can verify using the discriminant. The discriminant will give you a quick way of identifying, will my parabola cross through the x-axis? And if so, how many points, right? The discriminant gives you that information. Your discriminant is just the piece b squared minus 4ac. I am trusting that you all watched the video over the weekend, so this is not news to you. Okay, let's turn the page. All right, let's actually graph a quadratic equation. Okay, super cool. First things first, take a look at your equation. Y is equal to negative x squared plus 2x plus 3. I want to begin by identifying A, B, and C. In this case, would somebody share with me what is your A, your B, and your C in your equation? Anyone, go ahead and shout it out. In order they are?
X.
Well, what's the coefficient?
Negative 1.
Negative 1. Good. We want the leading term, that coefficient, right in front. Keep going.
Positive 2.
And?
Positive 3.
Perfect. So our leading coefficient is negative 1. So it's the value in front of the variable. Then for our linear term, it's a positive 2. And then our constant is a positive 3. So those are my coefficients. Next, I want to determine the direction of opening. Because I have a negative leading term, a negative quadratic, think negative, unhappy, frowning, opening downwards. Okay, so this is downward. What we have an idea here is that we know our parabola is going to look something like that. It's always helpful to have an idea of what your parabola is actually going to look like. Next, we want to find the equation for the axis of symmetry. As a reminder, your equation is x is equal to negative b over 2a. It is not enough to simply write negative b over 2a. Please don't do it. You must have x equals in front. So we're going to plug in our values. That means x is equal to negative b is 2. All over 2 times a is negative 1. So we have negative 2 divided by negative 2, which means my x is equal to a positive 1. Negative 2 divided by negative 2 is simply a positive 1. That is the equation for the axis of symmetry. Next, we want to calculate the vertex. Well, that's great. If I know that my x coordinate for my vertex is 1, so for instance, I know this already. What I don't know is what goes here. This is my empty space. I have to figure this out. Well, I have an equation. I'm being told that for my vertex, my x coordinate is 1. So it would suffice to say that in order to find y, I simply have to plug that into my equation. So I have y is equal to negative 1 squared, right? Keep in mind, you're only squaring this 1, not the negative. That negative is in front of the x, and the x is the only piece being squared. Be careful when you plug this in. plus 2 times 1 plus 3. We're simply substituting into our equation and then evaluating. So this gives me y is equal to 1 squared is 1, but we still have a negative in front. Negative 1 plus 2 plus 3. And then when we do the math, obviously that's going to give us a positive 4. So my vertex is 1, 4. Take your coordinate for the axis of symmetry, plug it in, calculate the corresponding y. Beautiful. This is great. We have a lot of information so far. We still need the x-intercepts and the y-intercept. Okay, so in terms of the x-intercept, we could attempt to factor this, or we could just use completing the square quadratic formula. I'm actually going to use a quadratic formula in this case. So I've got x is equal to, let's write down the formula, negative b plus or minus square root of b squared minus 4ac all over 2a. There's your quadratic formula. I would like you all to take a second and plug in your a, b, and c into your quadratic formula. Just take 30 seconds to plug in those values, and then I'll catch up with you. I'm going to catch up. Good. When you plug in your values, you should have exactly this expression. What I'll do next is I'm going to take care of everything that's underneath the radical sign. So we have 2 squared, which is 4, minus 4 times negative 1 times 3. So that means under the square root, I have a 16. So x is equal to negative 2 plus or minus square root of 16 all over negative 2. So far, so great. The awesome thing about this square root of 16 is 4. We can actually take the square root of this number since we have a perfect square, which is cool. Sorry that that highlighter just smushed my number there. So we have x is equal to negative 2 plus or minus 4 over negative 2. And now we have to split up our answers. So we've got negative 2 plus 4 over negative 2. So negative 2 plus 4, do that first, and then divided by negative 2 tells me that my first solution or my first x-intercept is negative 1. So I'm just going to write x equals negative 1, and we'll write the correct form in a second. Next, we want to do negative 2 minus 4 all divided by negative 2. So negative 2 minus 4 all divided by negative 2, and that's what's going to give us a positive 3. So it turned out this actually was factorable, but using the quadratic equation, we found our solutions anyway, so we didn't even have to waste time. Our x-intercepts are going to be written negative 1, 0 and 3, 0. Remember, in order to be an x-intercept, your y-coordinate must be a 0. Otherwise, how are you going to sit on the x-axis? You can't. Okay. Lastly, we need to find the y-intercept. We learned that in order to do so, we're going to make x equal to 0, which means we need to calculate the corresponding y. If I take my equation, y is equal to negative x squared plus 2x plus 3, and I make every x a 0, you'll see pretty quickly that your terms with an x will end up going away, right? They zero out. So this leaves you with 0 plus 0 plus 3, which means y is equal to 3. So your y-intercept is 0, 3. Okay, let's graph this. We're going to start with the axis of symmetry. When you draw the axis of symmetry, please draw a dotted line. Okay, and again, this is if you're doing this by hand. So our axis of symmetry, the equation is x is equal to 1. We learned that x equals 1 is a vertical line. So I'm going to go ahead and draw a dotted line right through 1. So this is x is equal to 1. That's our axis of symmetry. Next, I'm going to plot the points that we were given. So first off, the vertex is 1, 4. The vertex is 1, 4. And remember, it's going to be concave downwards. So we know it's going to be some sort of U shape facing downwards, opening downwards. Good. We have two x-intercepts. We have -1, 0 and 3, 0. Do you see how I am 2 away from the axis of symmetry and my other x-intercept is 2 away from the axis of symmetry? That's pretty cool. We also know that the y-intercept is 0, 3. So thinking about the fact that my y-intercept is just 1 point away from the axis of symmetry, that means thinking about it symmetrically, we have another point that's 1 unit away from the axis of symmetry. Now I can just connect the dots, make a nice U here. I'm going to do the best that I can, make this into a nice U shape. Do the same thing over here. And voila, there is your parabola. What questions do you have for me as you graph your first quadratic equation? What'd you think? What's your honest opinion of graphing parabolas? What are your thoughts? What do you think, Summer?
It's a lot of work.
It is, that's true.
To get there.
That's true, that's true.
Using to figure out like what method to use, I guess.
I will tell you, Summer, that you can actually always use this one. If for whatever reason you like the quadratic equation and you're like, you know what, why not? If I always want to find the x-intercepts, hell, I can do this every time, 100% of the time. Then Summer, I will tell you, go for it, right? Because 100% of the time you can use that, you know? Yes.
Okay, good to know.
Yeah, and it just depends on your style. Like for instance, Kim might be like, yeah, I mean, I like the quadratic formula, but I also like completing the square. And she might use completing the square, but the both of you will end up with the same result, which is super cool. The only thing that won't always work is factoring. So I kind of tend to advise students to go in either this direction or completing the square. Okay, awesome. Very, very nice. Yes, there are a lot of moving parts, but the great thing about this is that you're given all of the clues that you need to know exactly what this is going to look like. Let's turn the page and do another one. So we have y is equal to x squared minus 3x plus 4. I'm actually going to give you a few minutes. I want you to write the coefficients a, b, c, and I want you to follow each of these steps and see how you do. Okay, I would like you to do this on your own. So I'm going to give you just a few minutes to do so. And I'm going to pause recording right now. First things first, we are going to jot down our coefficients. So at the very top, A, B, and C, you should have had 1, -3, and 4. Because your leading coefficient is a positive number, it's a positive 1, the opening of the parabola will be upward. So when we look at this, we know it's going to be opening concave up. So like a smile. Next, we want to find the equation for the axis of symmetry. So x is equal to negative b over 2a. We have negative 3 over 2 times 1, which implies that my axis of symmetry is 3 over 2, which if that's weird to you, you can actually also consider this as x is equal to 1.5, right? If you took 3 divided by 2, you'd have 1.5. All right, something to think about in terms of, graphing. It's helpful to see our values in decimal form just so that we know exactly where this is. We then want to find the vertex. Now, with finding the vertex, I would actually recommend using the fraction form just in case our answer is something that is irrational, right? So let's go ahead and plug this in. We know that our x coordinate for our vertex is 3/2. We just don't know what our y is. So we have y is equal to 3 over 2 squared minus 3 times 3 over 2 plus 4. We know how to square a fraction. We just square each of the parts. 3 over 2 squared is going to be 9 over 4. Minus, we know how to multiply fractions. 3 times 3 over 2 is the same as 3 over 1 times 3 over 2, which means 9 over 4. And then we have plus 4. Look at what ended up happening. 9 over 4 minus 9. Oh my God, I wrote 4. Give me 1 second. Don't make this mistake. Thank you. 9 over 2. See, I caught myself. So we have 3 times 3 is 9, 1 times 2 is 2. So 9 over 4 minus 9 over 2 plus 4. Why don't we just plug it in? We could do the math by hand, or we could use our resources. So I have 9ABC4 minus 9ABC2 plus 4. Why not let the calculator do this? It gives me an answer of 1 3/4. So that would technically be 1.75. We could also change this to an improper fraction. So that's going to be 7/4. So y is equal to 7/4. I'm also going to write that that's the same as 1.75. That way it's helpful to us when we actually go and graph this. So our vertex is 3/2, 7/4, or 1.5, 1.75. Good. We want to go ahead and find the x-intercepts. I would recommend the quadratic equation, but you don't have to. We could complete the square. I'm going to use quadratic equation. So we have x is equal to negative b. Make sure that you're using parentheses if your b happens to be negative, plus or minus square root of b squared, make sure you use parentheses, minus 4 times a times c, all over 2a. Good. Let's take care of what's underneath the radical first. So negative 3 squared, that's 9. So we have 9 minus 4 times 1 times 4. So essentially 9 minus 16, which gives us a negative 7. So we have x is equal to, clean this up, negative 3, that's a positive 3. Plus or minus, underneath the radical, we have negative 7. And that's all over 2. Out of curiosity, what does that mean about the number of x-intercepts we have? What does this mean when our discriminant is negative?
There is no x-intercept.
Yeah, it's essentially floating above the x-axis or below it. It's not actually going to cross through the x. That's perfect. Thank you so much. We recall, though, that we can rewrite this using a complex number, using I. So we know that the square root of -1 is I, so I'm going to take that out. And that leaves us with square root of 7, which can't be simplified, and all of this over 2. So we can write our x-intercepts as 3 plus I squared to 7 over 2. and 3 minus I squared to 7 over 2. So these are my x-intercepts, but they're imaginary. So we're not actually going to graph those. They're just for our reference. Here are our x-intercepts. Next, we want to find the y-intercept. That one's really, really nice. It's just the constant term in your equation, but we know that the y-intercept is always 0 and then whatever the value is. So wherever you see an x, you're going to replace it with a 0, and you'll notice right away it's always going to be your constant, right? So in this case, y is equal to 4. So our y-intercept is 0, 4. Excellent. So the first thing we're actually going to do is we're going to start with our axis of symmetry, and that's x is equal to 1.5. So 1.5. So essentially, I'm just going to look at drawing a dotted line between 1 and 2. So I'm going to draw my dotted line as carefully as I can down the center in between 1 and 2. So this is x is equal to 1.5, or in essence, 3 over 2. Next, I'm going to plot my vertex. So my vertex is 1.5, comma 1.75. This is going to be a little bit rough because we're essentially guessing where this point is. We're going to try to be as accurate as possible, but because we're doing it by hand, it's not going to be perfect. But we can get pretty close. So not halfway through, but a little bit more towards our 2 mark. That's going to be our vertex. 1.5, comma 1.75. So not quite 2, but almost there. We have our y-intercept, which is 0, 4. Now think about how far we are from that line of symmetry. You want another point that's equidistant on the other side of the line of symmetry. So if you are 1.5 away from the line of symmetry, then we want to be 1.5 away on the other side. So this actually is very helpful because it gives us another point, which allows us to draw our U shape. Notice that our graph does not cross through the x-axis, and that's okay, but we knew that because our x-intercepts were imaginary. So this graph is essentially floating above our x-axis, which again, as a reminder, is not a problem. That's okay. And you're done. What questions do you have for me this time? Okay, you do have practice in your unit 4, so make sure you're trying that today while this material is fresh on your mind. Okay, it's going to be really helpful to you to do that. Excellent. Beautiful, beautiful, beautiful. Every time you graph parabolas, this is essentially the process you'll want to take. Determine the direction, axis of symmetry, find the vertex, find the x-intercepts, find the y-intercept, and then go to town graphing. Okay, notice in this case, I wanted to have that extra point so that I could make that U shape. I wanted it to look as close to reality as possible. So once I knew my y-intercept was 1.5 points away from the axis of symmetry, I knew that its mirror image, that point here, was also going to be 1.5 away. So just think mirror image on either side of the axis of symmetry. Good. Let's go ahead and turn the page because it sounds like there are no questions yet. So of course, we are ready to actually solve application problems. Notice that they're called maximum and minimum problems. This is very important to know. As a reminder, you'll know you have a max or a min at a vertex. So this point here is my vertex. For our previous page, when we look at the graph that, the parabola we graphed on page 22, my vertex is a maximum. So my vertex here is a maximum and my vertex here is a minimum. This is something that you need to consider as you move through these max and min application problems. So let me show you. So we're given the function negative 16t squared plus 48t plus 32. Really quickly, is this opening upwards or downwards?
Downward.
Down.
Yes, absolutely. So right off the bat, can you just draw this shape? So that means your vertex is a maximum. That's something to really think about. The vertex in this case happens to be a maximum. Okay, so that function describes the height in feet of a stone t seconds after it has been thrown upwards. So t is like our x. Do you agree? So x is being replaced by t in this case. So it's essentially t, which is time, and then f of t, which is height. So this is seconds, and this is height. It's often helpful to write the ordered pair so that you can interpret every ordered pair you are given. You can say, oh, the independent variable is time in seconds, and the dependent variable is height, because the height depends on how much time has passed. So for part A, it says determine the time at which the stone reaches its maximum height. Whenever you see this word, I want you to think vertex. I want you to think vertex, which means we have the equation. Generally, it's going to be x is equal to negative b over 2a. However, in this particular formula, x is actually being replaced by t. So you want to write t is equal to negative b over 2a. Would someone fill in the values in my equation? T is equal to, what would go here?
Negative 48 over 16, negative 16a. I'm sorry. No, sorry, 2 negative 16.
Yes, excellent, excellent, excellent. So we've negative 48 over 2 times negative 16. So negative b over negative b over 2a. So we do the math and we say, okay, well, this is negative 48 over negative 32. And if you take your calculator, negative 48 divided by negative 32 gives you a t of positive 1.5. So the stone reaches its maximum height after 1.5 seconds. The stone reaches max height in 1.5 seconds. Now, the interesting question, the follow-up is, well, what is that maximum height? You know exactly how to do this. What would I do with that 1.5? Go ahead, shout it out.
Plug it in.
Plug it in. Exactly, plug it in. So we have f of t, but t is 1.5. And everywhere we have a t in our function, we're going to replace it with 1.5. So negative 16 times 1.5 squared plus 48 times 1.5 plus 32. Type this entire expression into your equation. And when you are done, please share with me your result. Plug in this entire expression into your equation. What did you get? Yes, thank you, Phil. I've got one result. Anyone else find the solution here? Go ahead and shout it out. Yes, perfect, James, exactly. Yes, Oliver, beautiful. So that should have been enough time, hopefully, for everyone to see that your solution in this case is 68. So the maximum height, or the max height, is 68 feet. Make sure you include the units. The next part says how much time elapses to the nearest tenth after the stone is thrown until it hits the ground. If this stone is hitting the ground, that means your height must be 0, right? If it hits the ground, the height of the stone above the ground must be 0 because it actually hit it. So I'm going to write here that the height is equal to 0. And we recall that height is f of t. So let's replace that. That means that f of t is equal to 0. So we're going to take our equation, and where we see f of t, we're going to replace it with 0. So this looks an awful lot like something we've seen in the past many, many times. So we're going to write 0 is equal to negative 16t squared plus 48t plus 32. I would love some strategy. What might be something that will make all of our lives easier? What can we do mathematically? Go ahead.
Factor.
Yes. So out of curiosity, Jose, you're saying factor. What's my GCF? Do I have one?
16.
Yes, 16. Would I factor out just the positive 16?
Negative 16.
Aha. So notice what Jose said. We can factor actually. And what she's implying is that we can factor out the GCF. I'm going to take that one step further, and I'm going to say we can actually divide every term by that GCF so that our equation is much more manageable. So I'm going to take that negative 16, and I'm actually going to divide every term by negative 16. Instead of just factoring it out, I'm going to divide every term. Now, the great thing about this is that it actually is the GCF. Jose is right. Let's simplify this. So this gives me 0 is equal to t squared minus 3t minus 2. Awesome. Can I still factor this? Are there factors of -2 that when I combine them, I get a -3? Is it possible? No, it's not, right? Because a -2 would just be -2 times 1. And a -2 plus 1 is a -1. That's not going to give us a -3. So we can't factor, and that's totally okay. My advice to you, definitely use a quadratic formula. Let's do it. So t is equal to -b. Remember, you're using this equation here. A is 1, b is -3, c is -2. So -b plus or minus square root of b squared minus 4 times a times c all over 2a. Let's take care of what's underneath this radical. -3 squared is 9. So 9 minus 4 times 1 times -2, or 9 plus 8 is 17. So we have t is equal to, clean this up, -3 is a +3, plus or minus square root of, and we said that was a 17 underneath that radical, and then all over 2. My advice, just plug this in. Plug this in. We're looking for a value, right? We're looking for how much time actually elapses. And notice it says to the nearest tenth. So if I were you, I would literally take my calculator and I would say, okay, well, let's start with 3 plus square root of 17 and then divide that by 2. So my first solution is that my time is 3.6 seconds. So I'm going to write t is equal to 3.6. I'm also going to do the second one just to see what else I get. So 3 minus the square root of 17, and then divide that by 2. That leaves me with negative time. I'm going to throw that answer out because we cannot have negative time. So if you want, you could jot down t is equal to negative 0.6, but we're going to toss it out. That doesn't even make sense. So it will take 3.6 seconds for the stone to hit the ground. Okay, it will take 3.6 seconds for the stone to hit the ground. So the last thing we want to do is figure out from what height was the stone released. When you think about that logically, from what height was the stone released, doesn't that mean at the very beginning, when we first started this thing, when time was 0? So the idea here is that we want to know the height when we start this experiment, when time is 0, which is actually super cool because all you have to do is take time and replace it with 0 in your equation. You'll probably get used to the fact that what this is asking you for is the y-intercept, right? From what height was the stone released? So when you do the math, you find that these 0 out and you're left with 32. So the stone was released at a height of 32 feet. When time is 0, the height's 32. Look at this ordered pair. It's a y-intercept. So if we think about this logically, your function essentially looks something like this, right? So they toss up the stone and then whew, comes right down. Somebody chucked it up and it just followed that trajectory. We know that because essentially it was released at 32 feet and the max height is 68. Sorry if it doesn't look to scale. I just wanted to show you pretty quickly what's happening. Someone tossed it up and it returned to the earth, of course. Super cool. What questions do you have for me on this first max and min problem? My advice to you while you're thinking about this, my advice to you is when you're doing your homework problems, keep this handy. Keep your notes right next to you. That way, when you see questions like this, if you need a reminder, you have all of your little notes, you know, how to write the ordered pair, what the maximum implies, how to find maximum height. You essentially plug that in. What it means to hit the ground, and then what it means finding the height when it was just released, okay? Keep this handy. That's gonna be super, super helpful. So strategy for solving problems involving maximizing or minimizing. This is actually really interesting. So step number 1 is you want to determine the equation needed. So what quantity is to be maximized or minimized, right? And you want to express that quantity as a function in one variable. You want to write the function in the form ax squared plus bx plus c, so a quadratic equation. Once you have your function in the form of a quadratic equation, you can then find the vertex and then answer the question being asked. So let me show you what I mean by this. For example 26, it says, consider all pairs of numbers for which one number is 8 less than twice the other. Can we underline, highlight, whatever that is? This statement right here, I hope, jumps out at you. One number is 8 less than twice the other. Without even reading further, we're recognizing that there are two numbers here, right? We're also recognizing that we actually have a relationship. So let's think back to how we expressed our relationship. So I will recognize that one number and other number, that these are both the values in our relationship. We're told that one number is 8 less than twice the other. How do you think you can write that algebraically? How do you write 8 less than twice the other? What do you think? Don't be shy. What do you think?
2x minus 8.
I love it. That's perfect. And the order matters. Notice that it's 2x minus 8, not 8 minus 2x. Be very careful. Less than means you switch the order. What that implies about the other number is that it's just plain old x. So I want you to identify that that's your relationship. Okay, 8 less than twice the other, that means the other is just x. Find the two numbers whose product is as small as possible. When you think of as small as possible, I want you to think minimum. That's what you're looking for. What is the minimum product? What does product mean again?
Multiply.
Yeah, exactly. The product means you're going to multiply. So, okay, let's think about this. What we're being told to do is to take one number and multiply it by the other number. And that's going to be your function with respect to x. One number times the other number. We're just finding the product. So let me fill in what we have here. So we have f of x is equal to, and remember, we're just determining the equation that we need. One number is 2x minus 8. And the other number is just x. We are told to write the function in the form ax squared plus bx plus c. What that implies to us is that we want to distribute so that we have a quadratic function. So if I distribute this x to each of my terms, that means my function is going to be 2x squared minus 8x. Okay, so far so good. This is my equation. The next thing I want to do is I want to find the two numbers whose product is the minimum possible product. So when we see this word minimum, we need to think vertex. Okay, we need to think vertex. The really cool thing about this 2x squared minus 8x, what shape does this take other than the parabola? Is it opening upwards or downwards?
Up.
Yeah, it is. It's opening upwards. So we know that essentially it looks something like this, which means we can have a minimum here. We can have a minimum at this vertex, this point. So we need to find that. So let's go through the motions. X is equal to negative b over 2a. Let's plug in our values. What's b and what's a? B is?
Negative 8.
Yes, and a is?
2.
Perfect. So we have negative a, right? Negative b over 2 times a, and a is 2. So it gives us positive 8 over 4 which gives us a positive 2. So x is equal to 2. So we're trying to figure out the minimum possible product. So what we're noticing here is that we found that x was equal to 2. And when we think about our relationship, we have to consider, well, I wrote here that the other number is x. So the other number is simply 2, which implies that the one number is going to be 2 times 2 and then minus 8. So let's write this out. So one number, other number. I just found x, so let's plug that in. Other number is x, which is 2. And then our one number is going to be 2 times 2 minus 8, or 4 minus 8, which is negative 4. So find the two numbers whose product is the minimum possible product. So in this case, it's going to be 2 and negative 4. The two numbers whose product is the minimum possible are 2 and negative 4. And then it just says find the minimum product. Well, duh, multiply them together. Take your solutions, 2 and negative 4, and you get negative 8. The min product is negative 8, and you're done. This one isn't too bad at all, actually. I think the most important piece here is to establish the relationship. That kind of tends to always be the most crucial part. If you can establish the relationship, then everything else will fall right into place. So this is really, really important. You want to make sure that you write out how your pieces are relating to each other before you dive into the equation. That's always step number 1. Good. Very, very nice. We have one last application problem. Check this one out.
Can I see that page, please?
Yeah, for sure.
Thanks.
You're welcome. For the last problem that we're going to see, it actually has to do with looking at a rectangle and closing a specific area. So the questions you will probably see in your Lumen homework, they're just an expansion of this topic, right? I can't possibly cover every single type of max or min problem with you, but I wanted to give you the tools. So you may have to kind of sit with each of these problems and dissect what's happening, draw what's happening, visualize it before you actually go through these steps, okay? Jose, you're all set?
Yes, thank you.
You're welcome. So let's check this out. Take a look at what this says. You have 120 feet of fencing to enclose a rectangular region. That's very interesting to know. When you are told that you have 120 feet of fencing to enclose a rectangular region, what am I actually referencing here? What mathematical quantity am I representing if I'm enclosing a garden in fencing?
The perimeter.
Bingo. So that 120 represents the perimeter. That's interesting because we need to kind of keep that in mind. That has nothing to do with the area inside. It's the fencing around, which is really important to keep in mind. Okay, let's check this out. So you have 120 feet of fencing to enclose. So essentially this represents our perimeter. I'm just going to write that up there. Sorry, it looks sloppy. Find the dimensions of the rectangle that maximize the enclosed area. That's very interesting. And then once we figure that out, we want to know what is the enclosed area. When I asked you what the heck does that 120 feet mean, you said it was the perimeter. So here's what we're going to do. We're going to start by drawing our rectangle. The cool thing about this particular diagram is that it's not saying it's missing a side. If it were, it's not a big deal. But in this case, it's not. We have all 4 sides. We're going to label each of these sides. L, W, L, W. If I know that I have 120 feet of fencing, can you give me my equation initially? How do I use L and W to say I have 120 feet of fencing? How do you do it? What do you do with perimeter?
It would
Yeah.
be 120 plus 2L equals 2L plus 2W.
Okay, I love where we're headed. So you're saying, okay, add them, right? So that means you have 2 lengths and you have 2 widths, and that's equal to 120 feet of fencing, right?
Yes.
Beautiful. Keep in mind, we want to maximize the enclosed area. Okay. Can someone tell me what is the formula for the area of a rectangle?
Length times width.
Yeah, length times width. Very interesting. Somehow I've got to go from here to there. So check this out. If I want to essentially use this information to help me represent my equation for area in one variable, that means I want to solve for either L or W, and it doesn't matter which one. So I'm actually just going to solve for L in this equation, because then I can sub that into my area. So check this out. I'm going to start by subtracting 2W. That gives me 2L is equal to 120 minus 2W. I'm going to make a note here, solve for one variable. That's what we're doing. We're solving for one variable. And then I got to get L by itself. And we know that in order to do that, I'm going to divide by 2. So now I have that L is equal to 60 minus W. Are we okay so far? Okay. Now that I know that my length is 60 minus the width, I can actually replace my length in my area equation with 60 minus W, 60 minus the width. Let's replace L with that expression. So now I have that area is equal to 60 minus W times W. This is looking great because my goal in finding my equation, my goal is some sort of function where ax squared plus bx plus c is represented. I'm looking for a quadratic equation. Okay, so if I distribute, I get that my area is 60W minus W squared. That is my equation. It is not in descending order. So if you guys are not comfortable with that and you would rather see this in descending order, you could say also, or your area could be negative W squared plus 60W. If you wanted to see it in descending order, that's totally okay as well. Okay. The next thing we want to do here is we want to find the dimensions of the rectangle that maximize area. What does that mean I'm trying to find? Talk me through the next steps. I have to find the
Vertex.
Yes, I need to find the vertex. What's the formula for finding the vertex?
Negative B over 2A.
Good. Give me the entire equation. What equals negative b over 2a?
X.
Oh, X. Yeah.
So x is equal to negative b over 2a. In this case, what is x being replaced by? W. You see that? W is replacing x. So I'm going to write W is equal to negative b over 2a. Good. We have negative b is 60 all over 2a. A is negative 1. Good. So we have negative 60 over negative 2, which means my width is going to be a positive 30. So I'm going to write here that my width is 30 and my units are feet. So I've got 30 feet for the width. What formula would help me find my length? What do I know about my length? Phil, what do you know about your length? We actually defined length kind of in the beginning. We said that the length is equal to what?
60 minus W.
Exactly. Always go back to the information we derived. So we said that the length is 60 minus the width. Well, I know the width. It's 30. So that means my length is 60 minus 30, which means my length, guess what, is also 30. Perfect. So the dimensions that maximize the area are 30 by 30, 30 feet by 30 feet. Sorry that my dog is barking in the background. And then of course we find the maximum area. Can someone tell me what's my area?
$900 square feet.
Score, done. The max area is 900 square feet. We know that because 30 times 30, right? Area is length times width, so it's 30 times 30, which is 900 square feet. Done, that's it. That is it. I'm hopeful that you're seeing that this is not actually all that complicated. I think the biggest thing, and I'm going to say it again, is that relationship from the very beginning. If you didn't notice that 120 feet were referring to the perimeter, then there was no way to start this problem. You needed to recognize that referred to the perimeter, which gave you your initial equation, your 2L plus 2W equals 120. And then you just have to think about what your goal is. Your goal is to write your quadratic equation, which implies we need to solve for one of the variables and then plug it into your formula. So that way you can actually get your quadratic equation. That's what you are looking for when you maximize or minimize your application problems. Okay. Any other questions before we look at the last page and then we take a break? The last page will take me maybe less than 2 minutes tops. Okay, hearing none, let's take a look at that very last page. This last piece is just to show you what it looks like translating a parabola, like what the shifts look like. So for instance, here's our parent function. F of x is equal to x squared. This is what your x squared function will look like, your parabola. Now notice that if my coefficient, for instance, were a fourth, look at how wide my parabola becomes. And then when my coefficient, my a is 4, look at how narrow my parabola becomes. What this is implying is that as your leading coefficient gets larger, remember this is absolute value of a, so as that value gets larger, the parabola actually gets skinnier. right? So we went from a fourth, which is smaller than 1, so it's pretty wide, to a coefficient of 1. So here's what the original x squared looks like. And then when your coefficient gets larger than 1, it becomes more and more narrow, becomes skinnier. With your vertical translations, notice here again is your parent function. When I take my x squared and I add 2, look at what happened. It went from sitting on the x-axis to hovering 2 units above. It literally looks like you took your parabola and shifted 2 units up. Now notice if I take my original function x squared and I subtract 2 from my x squared, notice that I took the entire parabola and I shifted 2 units down, right? So what it's implying to us is that when the constant is positive, so like in this case, the number of units the vertex moves is upwards, right? So that's the number of units moving in the positive direction. It moves up. When it's negative, that vertex is going to move down, right? You're essentially moving it 2 units downwards versus 2 units upwards. That's the great part about this. You can identify what's happening by that constant on the outside. And now, in terms of your horizontal translation, that's what's happening inside the parentheses with the x. So notice here, here's my original. If I subtract 2 from x inside the parentheses, look at where it went. It started from the center, but then moved 2 units right, which is kind of crazy, right? Because doesn't this say x minus 2? And you're thinking, wait a second, I feel like maybe we should move it 2 units to the left. Well, recall that the reason for this is essentially this idea. When you solve for the variable, right, we have to add the x. So we actually move 2 units to the right. This is a positive 2. We move 2 units to the right. When we have inside the parentheses x plus 2, and we solve for x, it would be a negative 2. So it's 2 units to the left. That's what's going to give us our 0. So 2 units to the left. So when you are looking at the constant with x in the squared term, if it is positive, it's going to move, if it's positive, it's going to move left. If it is negative, it's going to move right. Okay. If it's a negative, it's going to move right. If it's positive, it's going to move left. And that concludes Unit 4. Excellent work. Very, very nice. We have one more unit to go. Let's take a 5-minute break. I will see you at 2. Let's just round up, do a 7-minute break in case you have to pee or poop. You never know. You never know. All right. I will see you at 10:30, and we'll spend the last 20 minutes of class taking a sneak peek at Unit 5. See you in 7 minutes.